The goal of this video recording is to review the basic ideas of limits of functions. So in our course we learned about limits of functions through the idea of a sequence. So if we are interested in this statement that the limit of a function as x approaches c has a value L, then the idea that we focused on was the idea of a sequence, that there's a sequence given by f of xk, and that sequence has to converge to L anytime the original sequence x converges to C. So I have a graph down below that illustrates this principle. So on the left I have a sequence. This is my sequence x. This is the independent sequence. So this independent sequence has a limit. It has a limit of 1. And so what we have is in the middle we have a function, and so this is the function we're interested in. Y is a function of x, and this creates a new sequence, our dependent sequence. Here's how the sequence idea works. If I think about my x sequence, the first value is at 0. And so if I think about my first point at 0, it creates a corresponding first point of my y sequence. If I go to the second point in my independent sequence, this gives me a corresponding second point of my dependent sequence. And so this process continues with my independent sequence generating a series of values for my dependent sequence, all of which are related through this graph of my original function. So what we have is we have a sequence of x that's approaching 1, and we're interested in the value of the sequence y that in this graph appears to be converging to a limit of 2. And if this is going to work for any sequence that I choose on the left for x, as long as x converges to 1, that the y sequence generated through my function will always converge to the value 2. We would say that the limit of my function for a sequence x converging to 1, the y sequence converges to 2. If I had a function, there are 3 typical questions that would be asked to see if we understand the idea of a limit. One question is simply to calculate the limit. Second question is to write down the formal meaning of the limit. That's the definition involving independent and dependent sequences. The third possible question is to actually prove the limit, or another way to think about that is to find the limit but do it step by step so that we're justified using true proofs or true theorems. In order to find the value of the limit, this is simply computational. And our typical strategy is to see what happens to each of the x's in the sequence, or in the function, to see what the formula will do. So this first step is we'll look at the form. In other words, we'll see what happens if we plug it in. Until we know that the form is going to be valid, we shouldn't write an equal sign. So let's write an arrow to remind us that we're just seeing what happens as all the x's approach 3. And so we have 3 different spots that our variable shows up. So we'll say, okay, the 3 stays a 3, x squared goes to 3 squared, 2x minus 5 goes to 2 times 3 minus 5, and the denominator, 5x plus 7, goes to 5 times 3 plus 7. Now we look at that and we ask, does this make sense, and would all the rules apply? And we verify, yeah, there's nothing goes wrong. I don't divide by 0, so everything's okay. So we just multiply things out. 3 times 3 squared is 27. 2 times 3 is 6, minus 5 is 1. Divided by 15 plus 7 is 22. And so our answer, the limit, has a value of 27 over 22. Now, if that original formula happened to be division by 0, then our limit rules don't apply. You can't divide by 0. So we would have to just double check and make sure that we didn't have an indeterminate form. Maybe it has an infinite value. To find the value of the limit of the function, we simply plug it in, see if it makes sense. If it does, our limit rules will justify that this is, in fact, our final answer. The second question would be to see if we remember and understand the idea of the limit definition. So again, as we did with our limits of sequences, let's review what the statement we're actually showing. So our question is, we are trying to find what is the formal definition of this equation, the statement that the limit of the function 3x squared times 2x minus 5 over 5x plus 7 as x approaches 3 has a value of 27 over 22. This problem is essentially a memorization problem. You need to know the definition. So the definition of this limit statement is that a sequence f of xk converges to 27 22nds whenever my sequence xk converges to 3, so long as my sequence never has the value of 3. That's really all it is. The idea that there's an independent sequence, xk, is converging to the value 3 given by the limit, and that my dependent sequence converges to the value of the limit. The third question is to actually justify the limit. So this is more than just finding the value. This is using limit rules every step of the way in order to find the value of the limit. Sometimes if you've already shown the limit, it's to prove your limit. Or if you haven't found the limit, it might be asked to compute the limit justifying every step. They're really the same thing. So to do this, what we were going to do is we're going to create a proof, and each step of our proof has to be a limit statement that we know is true based only on previous limits we found and basic limit rules. Alright, so we put down the limit that we're trying to get to, and now let's begin. We know that the sequence x approaches 3 because that was given to us by the limit statement. X squared approaches 9 because we're using a product. That the limit of a product is the product of the limits. And in step 1, we use the limit of x approaching 3. So x squared approaches 3 squared. 3x squared approaches 3 times 9, or 27, because of the constant multiple rule. A lot of students want to use a product rule here, but we did not actually find the limit of a sequence 3. Instead, we found the limit of x squared, and we're simply multiplying it by a constant 3. Another constant multiple comes when we take 2x. X approaches 3, so 2x approaches 6. Again, this is a constant multiple rule. This time, we did a constant multiple of the sequence calculated in step 1. The last constant multiple we will need is the limit of 5x. As x goes to 3, 5x goes to 15. Again, we did a constant multiple, 5, times the sequence we did in step 1. Two more sequences that we need are constant sequences. The sequence 5 is a constant sequence, 5, 5, 5, and so on. That has a limit of itself. Similarly, the sequence 7, that's always 7, has a limit of 7. In both of these, we're calculating the limits of constants. These are elementary limits that don't require any previous limit calculation. We can now combine some of these. 2x minus 5. 2x was calculated in step 4, 5 was calculated in step 6, and we're simply calculating the difference. 2x went to 6, 5 went to 5, so 2x minus 5 goes to 1. This is the limit of a difference. The limits that were required to calculate that difference occurred in step 4 and step 6. The sequence 5x plus 7, the parts were calculated in step 5 and step 7, and so if I add them, I get a value of 22. This is the limit of a sum. The second to last step is to finish calculating the limit of the numerator. We've already calculated the limit of 3x squared and the limit of 2x minus 5. We now need to multiply those answers, 27, using the limit of a product. 3x squared's limit was calculated in step 3. 2x minus 5's limit was calculated in step 8. So the product is 27. And now our final step is to do the quotient. 3x squared times 2x minus 5 was calculated in step 10 with a limit of 27. 5x plus 7 had a limit of 22 calculated in step 9. And so the limit of a quotient is the quotient of the limits. Our final answer is 27/22. We have now successfully proved that the limit of our function as x approaches 3 is 27 over 22 using limit rules one step at a time.